Okay, so we were just about getting ready to start looking at the set identities that are very, very similar to the laws of logic that we've already seen. Okay, so we have the idempotent laws. So if I take A and I union that with A, so I take all of A and all of A and put them together in a bag, what will be in the bag?
A.
A, yeah, so that's the idempotent law for a union A, and if I take A and find out everything that it has in common with A, it will be A, yeah, because they have all, A has all the same elements as itself. So the where A overlaps with A is everywhere. It's all of A. Okay, so those are our idempotent laws, very similar to what we've seen with logic. Okay, the associative law, if I have a bunch of unions together, I can change the placement of the parentheses. Instead of grouping the first two, I could group the second two. So notice in this one with the associative laws, both of these are unions. They're both the same operation. When we come down to the distributive law, you'll see the difference. One of them is a union, one of them is an intersection. It's different from this law. Here, all of the operations are the same, all unions. Okay. We also have associative law for intersection. So once again, both of these are intersection, and so I can change the parentheses. Oops. And it doesn't matter which order I do the intersections in. Okay. Then the commutative law. So commutative law, what does that tell me? If I can do A union B, that would be the same as what happens when I apply the commutative law? Yes, B union A. It doesn't matter what order I do them in. So I can change the order and do B union A, and it will be the same as A union B. Same thing applies to intersection. So B intersect A will be exactly the same as A intersect B. Doesn't matter which order. Okay, and then we have the distributive laws. So notice, here the operations are different. They're not the same. Associative, they have to be the same. With the distributive, they're going to be different. So just like we do with, multiplication and addition, or what, okay, or with disjunction and conjunction, the same kind of thing is going to happen. So we're going to take the first one and use this operation. Okay, so we're going to do A union B. Okay. And then we'll take this operation and we'll do A union C. So think if this were multiplication, we do A times the first one, and then we use plus A times the second one. It kind of works the same way, just different operations. It's not multiplication and plus, it's intersection and union, or union and intersection. Over here, we'll do A intersect B, and then this operation, union, and then distribute the A to the second one, A intersect C. So just the way you expect the distributive law to work. Okay. So identity laws, identities are always some operation you apply and you get the same thing back. Right? So we're talking about the identity property of multiplication. You have to multiply by 1 to get the same number back. For addition, you have to add 0 to get the same thing back. If you're doing, logical operations, you would have to AND something with true to get the same thing back. Okay, so here I start with A, and I want to apply an operation and get A back. So what would I have to union A with so that I don't change it and it's still A? Well, that's the idempotent law. Yep. Yes, the empty set, the null set. Okay, so if I take A and throw it in a bag with nothing else, okay, over here for the identity law, I have A, I want to intersect it with something and get A back. The idempotent law is when I intersect it with itself. It's got to be something different. Okay, so what could I intersect A with and guarantee that I'm going to get A back? The universal set. Good. So remember that the null set is sort of like a logical false, right? So if you think about, if I took A and ORed it with a logical false, I would just get A back. This is kind of like an and this is universal set is like true. Everything's in that set. So this is like A and true is A. So they're very similar in nature. So this acts very much like false, this acts very much like true. Okay, with that in mind, we have our dominations law. If I take A and I intersect that with the empty set, what do those have in common? Empty, yeah. So the empty set's got nothing in it. So here, the empty set dominates. There's nothing in it. You try to see what it has in common with anything, it's just going to be the empty set. Okay. Over here, we have A, and I throw it in a bag with the universal set. What's in the bag? The universal set, right? That dominates. It's got everything in it. There's no way to not get the whole thing. That's a U. Okay. Then we have the complement laws. If I take everything in A and intersect that with everything that's not in A, what will those two things have in common?
Nothing.
Absolutely nothing. So this is going to be the empty set. Okay. And then along those same lines, the complement of the universal set is the empty set as well. The universal set has nothing. If I take the complement of nothing, has everything. If I take the complement of everything, I get nothing. And then over here, if I take A and I put that together with everything that's not in A, what do I get? The universal set. Okay. And then the complement of the universal set is also the universal set. So the universal has nothing. If I take the complement of nothing, that's everything, and everything is in the universal set. Okay. And we covered De Morgan's laws last time. So De Morgan's laws, very much like with sets, if I have a complement over some kind of operation, some union or intersection, I'm going to do the complement of the first one, change union to intersection, and the complement of the second one. Okay, same kind of thing happens over here. I'll take the complement of the first one, intersection changes to union, and complement the second one. Okay. I feel like the absorption laws are much easier to understand with sets than they are actually to understand with trues and falses in logic. Okay, so if I took A and intersected it with B, that would be everything that's common to both A and B. And now I take all that stuff that's common to A and B and put it together with A. What am I going to get? Maybe it's not as intuitive as I thought. Let me draw a picture. Okay. So here's A and B. Let's say this is A and this is B. And I'm going to take A intersect B. That's all this stuff that's common to A and B. And then I put that together with A. What's that going to be? Just A, right? Because all the stuff in A and B is already in A. And now I'm going to take that stuff that's in A and unit it together with A. Of course I'm going to get A, right? Because all the stuff that it was in here was already in A. It was also in B, but it's already in A. Okay. This one, I take stuff. Now this is everything that's in both A and B. Okay. And now I'm going to intersect that with A. What am I going to get? You're going to get A again. Let's draw a picture of that one. Here's A and B. Okay, so A union B is all of this stuff. And then I'm going to say, all right, well, what does all of that have in common with A? So here's A. What does it have in common? Well, just A itself. That's the only stuff that's in common. Okay. And this one's easy. Double complement law. The complement of A is A. Okay. So, now that we have these laws, we should be able to prove stuff about set identities without having to draw a bunch of pictures. We can just apply the laws to prove things about them. So we want to keep this in handy so we can use them. Okay. So let's see. Let's see how much of this we can get on here together. All right, we got most of it there. All right, so we'll start with the first one. So we have B union A, and we're going to intersect that with not B union A. So we'll start with the left side, and then we'll try to show that that's actually the same thing as A. So this is our given, or our hypothesis that we start with. And we want to apply various laws. Okay. Any ideas what we might do to rewrite this in an equivalent form? If you don't have ideas, I'll rewrite it and see if you can come up with an idea. Oh, sorry. Any ideas? Yeah, the distributive law looks good. So this distributive law, as long as we have some, so, you know, if you look at it, it looks kind of like one of these things. We have to look, what do we have as our common term that can be kind of like factored out? What's our common thing that can be factored out? A, yeah. Okay, so you might want to I'll rewrite this for those of you that have trouble seeing it. So if I rewrite this as A union B intersect A union B bar. Okay. What reason would it be okay for me to do that? Yeah, the commutative law. Okay. And now it's a lot easier to see that we can apply the distributive law because it's written with A as the first thing, like our distributive law is. Okay, so we have this common A that can like sort of be factored out like we would do. So notice the operation in here that's being done. So that would go here. And then we know that we did A union with the first thing, so that one goes here. And then this operation in the middle. And then to get this one, we had to do A union second thing. So notice if we apply distributive law, I'll get A union the first thing, which is there, intersect A union the second thing. That's over here. So that is an example of the distributive law. Okay. That was probably the hardest step. Now, is there any part of that that we can simplify? So let's look at domination. That's an idea. So do we have an A intersect the empty set or an A union the universal? No. Which complement law. Eventually, I think we'll get to maybe domination, or we'll see. Okay, so we do have B intersect B bar. That's like this one, A intersect A bar. So we can replace this B intersect B bar with the empty set. Okay. So this is the complement law. Okay, and now how about A union the empty set? Identity, yeah, so we didn't actually get domination, we got identity. So the identity tells us that this is just A. And that's what we were hoping to show that it was equal to, was A. So that's the first one. Okay. Okay, the second one we have, okay, not A intersect B complement. Okay. So hopefully you can see those all. Any ideas about what we might want to do first? Yep. Let's do De Morgan first, because we got this big complement over top of an intersection or a union, so that is the natural one to use. So we're going to do the complement of the first, change the intersection to union, and then the complement of the second. Using De Morgan. Let's put our given up there. Okay. This is one short and sweet. Okay. So what should we apply? What rule should we apply next? Well, I think you can't even see it, but you probably know what it's called. What one do we apply next? The double complement. Okay, so not, it's like not B, or complement B is just B. And that's what we were hoping to get, so we're already done. Okay, and the third one. All right, this one is A intersect B intersect not B. Okay. All right, which one do you want to, let's see if I can move these up. Yep, you can see them all now. All right. What do you feel like you want to do first? Yeah, complement law. So complement law, again, we see this something intersected with its complement, so we can replace that with the empty set using the complement law. And then A intersected with the empty set is domination. Okay, and that will give us the empty set, and that's what we were hoping to show, that it was the empty set. Okay. So these are very similar in nature to what we saw with the laws of logic. They're very, very similar. So if you can do them with laws of logic, I doubt that you'll have any problems doing them with sets. Okay. Now there's one more law that's not listed. I'm going to keep this one handy because we will need those as well. One more law is the set subtraction law. Okay, and that states that we can change set subtraction A minus B into A intersect B bar. And to look at why that's true, it's useful to look at the Venn diagram. So remember, set subtraction, you would start with the whole set A, and then you would remove from that set anything that was in B. Okay, so if I would start with this whole set of A, and all this stuff that was in B, I would take all of that out. Okay, and so what's shaded here is A intersect B. Notice that is exactly the same thing as intersecting A, which is maybe my little, this is sometimes helpful to look at. I saw another marker, yeah. So if we take A, which is right here, and intersect that with B bar, which is all of this stuff out here. Okay. What do we have in common? Well, the only stuff that's in common to both, whereas both, I guess I should have put it, all of this in purple as well. The only part that's both purple and green is right in here, right? Okay, so it's that same thing that was shaded there originally. Okay. So you can see that A minus B and the A intersect B complement have the same Venn diagram. They'll have the same elements in them. Okay. So now that we know that definition, we can use that as another law in addition to these laws to help us prove other set identities. All right, so let's try these ones. All right, so let's see, I'll start up here. So I'm going to start with this A minus, and then B intersect A. So that's what we're given, and we want to show that's the same thing as just plain old A minus B. Okay. So when I see this subtraction, it's nice to change anything. Notice, like, this big set of laws only has unions and intersections in it. So if we can change from subtraction in terms of intersections, okay, then we can just then rely on all of these laws. So we can, as soon as we see that subtraction, we know we want to get rid of it and convert it. So if I have one set minus another set, it's the first set. So here my first set is A, intersect the complement of the second set. Okay, so this is what I'm subtracting, so I'm going to intersect with the complement of that set that I'm subtracting. So I'm just using the set subtraction law. Okay. And that's nice because now everything is written in terms of unions and intersections, and we can go back and use our good old set identities over here. Okay. So, what do you feel like the very first thing that you want to do? Or the very second thing, I guess. We already got rid of, our very first thing is to get rid of the minus. So what law do you feel like you want to apply right now? De Morgan, good. So let's go with De Morgan. Okay. And I'm going to put this in parentheses so we make sure that we preserve our order of operations. So we're going to do the complement of the first set, and then change the intersection to union, and then the complement of the second set. Notice how important those parentheses are, because if we didn't use them, then we might be tempted to think that we could do the A intersect B first, but we can't. Okay, this has to be done first, that the parentheses are, essentially right there. Okay. All right, now that we've done that, these operations are different, so what do you feel like you want to do next? Yeah, let's do the distributive law. So we're going to take the thing on the outside A and intersect it with the first one. So A intersect B bar. And then put this union operation in the middle. And then distribute the A to the second one. So A intersect A complement. Okay. Well, this one looks promising. What's A intersect A complement?
Nothing.
Nothing, so that's the empty set. And what's the name of the law that we use there? Complement law, good. I heard it very quietly. All right, and now we have a set unioned with the empty set. What law can we apply to that one? Identity. Okay, so we know if we take a set and add nothing to it, we just get that set back. Okay. All right. And now it's looking like there's not a whole lot that we can do. And let's go back and see what we were trying to prove. We were trying to prove that this was equal to A minus B. So A intersect B bar, look at that. A intersect B bar, what is that equal to? Well, that's equal to A minus B by the set subtraction law. And now we have what we needed. Try the next one. So we have A union B minus A. And we want to show that's actually the exact same thing as A union B. Okay. So of course, when you see that minus in there, probably the first thing you want to do is get rid of it so you can just deal with these laws and not have to worry about the subtraction. So let's do the set subtraction law and replace that with, okay, well that's always the first set intersect the complement of the second set. So this time our first set is B, and we intersect it with the complement of the second set. So the complement of the second set will be A complement. So there's our set subtraction. Okay. Now what do you want to do? Distribute. Okay. So we'll do A with the first one, intersected A with the second one. Oh, and this is nice. A union A complement. I guess you can't see. That is, what is it?
Nothing.
Ooh, a union.
Oh, union.
Yeah. Everything. That's the universal set. Okay, and so what was that law? Yeah, it's still complement. So here it is. A unioned with A complement is the universal set. So it's still one of the complement laws. Okay. All right, and now we have a set that's intersected with the universal set. So when we take a set and intersect it with the universal set, we just get
Identity.
yeah, that's the identity law. We just get that set back. So we get A union B back. That's the identity. Okay. And good. That's what we were hoping for, so we're done. And then the third one we'll just do right underneath it. Okay. So we'll look at A minus B minus A and show that that's the empty set. Okay. So with all these minuses in here, we probably want to get rid of those using the set subtraction law. So let's do the one in parentheses first. Okay. Well, let's not. Let's do this one first since it's sort of outside. Let's do this one first. Okay, I think it'll be easier for us to see. So when we have two sets are subtracted, we want to take the first one, intersect the complement of the second one. So we're going to do the first one, and then we're going to intersect that with the complement of the second one. I think it'll be easier to see that way. Okay. All right, and we still have this subtraction. Let's get rid of that one too. So let's apply set subtraction again. Okay. And so for this one, we're just going to leave that one as it is. But over here, we're going to take the first one, which is A, and intersect it with the complement of the second one. And now probably what you notice is that these are both intersections. Okay. And so if you were doing all these intersections, which ones would you like to intersect first? Yeah, we'd like to get A and the complement of A. To be like really formal though, so let's just make it this, put it like this, so that when we change the parentheses, A and the complement of A will be right beside each other. Okay, so why is it that I can change the order of those two?
Associative property?
No, that's it. Changing, so A used to be first and now it's second. So what's the one that says I can change the order? The commutative. Yeah, so that's the commutative. Okay. And now I'm going to apply the associative and say, okay, these are all the same operators, but what I would really like is to group A and A complement together, because those ones I know something about. So there's our associative. Okay. And then what is A intersected with the complement of A? Nothing, I heard, so that's the empty set. Okay, and then that's the, which law? Complement. Okay. And then a set intersected with the empty set is the empty set, and then what's that law? Domination. You gotta admit these are kind of fun.
Yeah.
Yeah. Okay. So I like these. Okay. Okay. Moving on to Cartesian products. These are kind of fun too. I don't know. I like the set identities better, but these are fun too. Okay, so the next operation we're going to look at is the Cartesian product of sets. Okay, so when we do a Cartesian product, we're going to be concerned with getting ordered pairs. So let's review what an ordered pair is. So we have an ordered pair. That's a pair of things, x and y, two things, it's a pair. Okay, and they're ordered. So x comes first, y comes second. Whenever we have an ordered pair, we put parentheses around the ordered pair. We list the first thing first, comma, second thing second. Okay, we're very familiar with that kind of notation. If you think about a Cartesian coordinate system where you have a bunch of points in a plane, you have an ordered pair that tells you a location. Oh, like you do x first, like I go 2 in the x direction, and y comes second, I go 3 in the y, and that gives me a unique spot in the Cartesian plane so that we all are talking about the same location in the Cartesian plane. Okay, so it's very important that these are ordered. Whatever comes first, we know, is going to be the x direction. Whatever comes second is the y direction. So whenever we see parentheses around two things, that's ordered. When we see curly braces around two things, that's a set, that's unordered. So notice the difference. They look kind of similar in nature, but they're not. So 2, 3 on the Cartesian plane over here is very different than 3, 2 on the Cartesian plane, which is here. These are different locations. They are not the same thing. Okay, the order matters. Whereas the set containing the elements 2 and 3 is exactly the same thing as the set containing the elements 3 and 2. Order is not important. Okay, so parentheses, we're talking about an ordered pair. Order matters. Curly braces, throw order out the door. It doesn't matter at all. Okay. So, a Cartesian product of two sets is very similar to what we think about in a Cartesian plane. We're going to get this little x between, that denotes the Cartesian product. Okay, so if I take one set A and another set B and I do the Cartesian product, I'm going to get all of the order pairs A and B, where the first item in the ordered pair comes from the first set, A, and the second number in the ordered pair comes from the second set. Okay, so it's all possible ordered pairs that I could find, okay, where the first one is from the first set, the second one is from the second set. Let's do some examples. Okay, so here's a set A. It contains two things, the letter A, the letter B. The set B contains 3 elements, the empty set, a set containing the letter B, and the letter C. Okay. So if I do the Cartesian product, I'm going to get the set of all possible ordered pairs where the first thing in the ordered pair comes from set A, and the second thing in the ordered pair comes from set B. Okay. So it's going to be a set of ordered pairs. So I'm going to give myself, a little bracket to say that it's a set. And then every single element in the set will be an ordered pair. All right, so let's think about my first ordered pair. All right, well, I could have an ordered pair where two things. So A is from the first set, so I could put A there. And then the empty set is from the second set, so that could be a possible second item. So now I have an ordered pair where A is the first and the empty set is the second. All right, so that's definitely there. Well, there are other ordered pairs that have A as the first element. So I want to go about this systematically. And I would maybe first list all of my ordered pairs where the first element is A. So I could have the first element be A where the empty set was the second one. Okay, I already covered that one. Or I could do the set containing B was the second one. Or I have another option where A is first and the C is second. So those are all the options where A is the first, okay, in the ordered pair. And I've exhausted all options from B. And of course, we've also got ordered pairs where B is the first in the ordered pair. And now we have to exhaust all the options. Okay, so the second one has to be from B, so it could be the empty set. We could have an ordered pair where the first element is B and the second element is the set containing B, because that's from set B. Or we could have the ordered pair where B is first and C is second. So this covers all the possible ordered pairs with A first. This covers all the possible with B first. That seems to exhaust all possible ordered pairs. Okay, so we can and that is the end of our set. So notice that our set is a set and its only elements are ordered pairs. Ordered pair, ordered pair, ordered pair, ordered pair, ordered pair, ordered pair. Let's do B Cartesian product with A. So notice there's a subtle difference here. This time, when we have the ordered pairs, the first item in the ordered pair has to come from set B. So these elements from B are going to be the first in our ordered pairs, and the second has to come from set A. So these will be our second elements. Okay, so once again, probably just go through it in a logical order. Say, all right, well, I'm going to have ordered pairs where I'm going to have the empty set as the first element. Okay. And now all possible second items are A or B. So I would have the empty set with A, and I would have the empty set with B. Those are all my options with the empty set as the first. All right. Well, the set containing B is also there, so that's an option as the first item in my ordered pair. And that could go with A, or that could go with B. So those are the only possible ordered pairs that have the set containing B first. And then finish it out with the ordered pairs that have C. So C could be first, A could be second, C could be first, B could be second. So one thing to note here is that A, the Cartesian product of A and B is not the same as the Cartesian product of B and A, right? These are not the same sets. Now, a lot of, because this ordered pair and this ordered pair are not the same. This ordered pair and this ordered pair are not the same. The order matters. Okay, so even though a lot of the pairs kind of are matched up, they're in a different order, so they're not the same set. Okay. We can also do the Cartesian product of a set with itself. So the notation, if I do like A squared, that means A Cartesian product with A. So it's still going to be ordered pairs where the first in the ordered pair comes from set A and the second also comes from A. Okay, so if I were to make an ordered pair, well, A could be first, and what are all the possibilities for the second? Well, anything from A. So A could be there or B could be there. Those are all the possible ordered pairs with A first. And then I would need all the possible pairs with B first, because B is in A. So B first with A, or B could come first with B. So it's every possible ordered pair where both of the items in the ordered pair are from set A. Okay, so looking at some properties of a Cartesian product. First of all, is the Cartesian product commutative? No, definitely not. So notice up here, we had A cross B and we had B cross A. Those were two completely different things, right? So it's definitely not commutative. Okay. How about this? What is the cardinality of the Cartesian product of A and B? How could I find that?
Cardinality of A times the cardinality of B.
Good. The cardinality of A times the cardinality of B. So notice, this one's going to have to be matched up with all of this. Okay. This one's going to have to be matched up with all of this. So 2 of these times 3 of these, we're going to get 6, right? We got 6 here, we got 6 here, we got 4 here. Definitely. We just have to look at the individual sets, how many pairs I have to just multiply the 2 cardinalities. Okay. So if you think about the Cartesian product of real numbers crossed with real numbers, that's telling me it's time for me to finish up because we need to take a quiz. Okay, so if we are doing real numbers cross real numbers, going back to our Cartesian plane, that's what the Cartesian plane is, right? Every possible set where I've got a real number and a real number is some location in the Cartesian plane. That's what R cross R is. This is just all points in the Cartesian plane. We will finish up our discussion of Cartesian products and end our discussion of this chapter next time. Before next class, we need to do the whatever section on set identities. Is that whatever it is? I'll post it in Zybooks. 2.5 is it? Okay, thank you. Yes, 2.5 because this Cartesian product is 2.6. I think. Thank you.